Welcome back, everybody, to another episode of Meti with a Fantastic Researcher. And today we have Eric, who's going to be teaching us about semantic sensitivities and inconsistent predictions and measuring the fragility of NLI models. Eric, thanks a lot for coming. We really appreciate it. Sorry, I did not pronounce your family name because I was afraid I'll make a mistake doing that, although you just taught me how to do it. So I'm sorry about that. But the floor is yours, and I'm very excited to learn from you.
Thank you very much for having me. No problem with the surname. Okay, so I'll be presenting on the topic where we try to dive into when, how, and how to measure the semantic sensitivities and inconsistencies of the models. And first of all, we have to dive in a bit of a definitions. So about language models and semantics. So what are semantics? What is semantic comprehension, and why is it important at all? So uh, in pure definition fashion, semantics is the branch of linguistics concerned with meaning, and we in particular are focusing on compositional semantics. Essentially, how do the words come together in order to create this notion of relations in between them and meaning in general. And obviously, it is important. It is important to understand how do the models how much are the models capable of this type of a task, and how much are they incapable or sensitive to semantic comprehension and semantic changes. So the general question is, do language models have semantic comprehension? And although there have been attempts to probe languages in terms of compositional semantic capabilities, it's a bit finicky. Essentially, we don't really know if there is an emergence of them or not. And people have been trying to use proxy tasks like analyzed, superglue, benchmark, and others, which we'll cover later on, in order to say, yeah, if you're capable of this, then you're likely capable of semantic comprehension. However, we showed that strong performance on this type of text does not exactly cause semantic correlation as semantic comprehension, and is even not vaguely correlated in a lot of instances. So the two schools of thought are that models appear to understand semantics and that models do struggle with semantics. Obviously, if we have a data set and we can obviously train on a proxy task and claim, yeah, we have achieved AGI and we have achieved semantic comprehension. So that's an argument for the point. However, in a lot of cases, we do know that models even don't understand lexics and the importance of lexics in a lot of cases. So there has been a study where let's shuffle all of the words and the model was still getting the answer right in a lot of the cases, meaning it does not really pay attention to the words. It was finding some type of hacks to find the answer. So there hasn't been a very systematic way to measure, to assess, to analyze models up to this point. So we have to actually understand what and how to probe. So our hypothesis is, let's take a set of models that are trained in understanding of semantic comprehension. Essentially, the proxy task is used in order to induce the semantic comprehension inside of them. And by proxy task, we mean natural language inference, as you see on your screens. There are several types. It's a pairwise classification task where, given a premise and a hypothesis, we try to understand if one contradicts the other, one entails the other, and one is neutral to the other. The basic premise of this being, if the model is capable of this, then it should pay attention to the meaning of the sentence and not just finding hacks, which we kind of show is not true. So we propose to test pre-trained language models, LLMs, that are tuned on this analyte datasets to see the extent of their emergent semantic capabilities. We also propose a framework for testing semantic sensitivity within this NLI models by creating semantics preserving surface form variations of the hypothesis. We will actually cover that later. So, and we do a set of ablations in order to show what's the extent of the sensitivity, how sensitive the models are, how insensitive they are, and so on and so forth. So Our contributions are that we propose like a novel way to do it, to do all this activity. Then we systematically study the influence of this phenomenon on inconsistent predictions across various transformer variants. And then we show the effect is persistent across like a variety of setups, namely in domain and out of domain. We check for model size, we check for model scale, we check distillation setups, and we'll cover everything in a bit. So this is our setup in general.
Eric, may I ask a question?
Yeah.
So is it fair to say that, if I understand correctly, you are trying to argue that doing next token prediction as losses to train PLMs is not effectively leading the PLMs to learn about semantics? Is that fair?
So we're not covering generative models. We're covering transformers trained for classification tasks.
Oh, okay,
And we
I see.
say, even if you are trained on a data set that should involve semantic understanding, we kind of show that you don't get that. You just get like good performance on the data set, but not the good part of the semantic understanding.
Right, makes sense. Yeah, I mean, even it's quote unquote easier task than like pre-training with the next token predictions for generative. I see. Yeah. Okay. Okay. Got it.
Exactly.
Okay. Understood.
We have this like very straightforward twofold setup, where one part of it is adversarial semantics preserving surface form variation generation. It is like a very long sentence, but I kind of word it explicitly like this, and there is an explicit reason for it, because we want to have examples that are logically equivalent to the original hypothesis. However, they have some different surface form variations that should not impact the outcome. So this is like where our general hypothesis comes in. We postulate that semantic understanding must minimally involve understanding that if the two sentences are the same, then they're the same, and if the two sentences are different, then they're different, in very layman terms. And for this very purpose, we say, okay, let's actually generate logically equivalent hypothesis, a logically equivalent like adversarial hypothesis, we can call it, from the original. How we generate, we'll cover like in the next slides, but let's say we're able to do it. After we create like a set of this adversarial hypothesis, the idea is that because it's logically equivalent and only difference in like some surface form, that the NLI model that is trained for that particular task should not flip the label. Essentially, it should give a consistent prediction as it did for the original pair. And like a bit of a spoiler, it turns out it's not the case in a lot of the stuff. That's the general premise of our test, and we have further analysis to cover as well. So how do we essentially do the first part is like the important question. So we're given a pre-trained language model M that is trained for textual entailment. Textual entailment is the same as NLI, and a standalone hypothesis H. So a hypothesis can be like any type of a sentence. It doesn't really matter. Before introducing semantic variations, only the samples where the model was originally correct are taken. So we don't really want to look into examples where a model was wrong, because if, for example, we create a variation of that and model is still wrong, that doesn't really tell us much. That is why we kind of want examples where we know model was confidently right. Let's see if it remains confidently right. So that's why we sample only the correct set of answers that model got initially. So in order to introduce this like semantic surface form variations, we use a large language model, large language model G, and we just like ask it to paraphrase minimally over the original hypothesis H. In of itself, this is definitely not enough, and this is prone to be a faulty way. Because first of all, we have no way to evaluate if the sentence is actually logically equivalent, if there's hallucinations in the next sentence, and so on and so forth. So that is why we impose a condition. We say, because NLIs are taking this pairwise input of two sentences and like understanding if they entail each other, are contradictory to each other, or neutral to each other, we say, okay, the assumption is that at least in the eyes of the NLI model we're testing, the original hypothesis and the generated hypothesis should have this like bidirectional entailment. Essentially, hypothesis should entail the adversarial hypothesis. Should entail the adversarial hypothesis and vice versa. The adversarial hypothesis should entail the original hypothesis, which in more like logical terms, from math logic and from some literature on language, is called like logical equivalence. That is how we essentially check for it. So we generate until that condition is explicitly satisfied, and then we can say, okay, now we have examples that in the eyes of the model are logically equivalent because we have predictions from the model. So we generate like several examples, k examples for each of the hypothesis h. So we have this like set for testing. So of course, we do evaluations in order to understand if this method is good. So we do automatic evaluations on different data sets, and we see that like we have a very high fuzzy token match. Like that. Yep.
Eric, sorry to interrupt again, but
No problem.
can you kindly go back one slide?
Of course.
Yeah, I didn't get how do you decide that you actually, like the condition that you decide that actually, oh, okay, these two sentences, the original hypothesis and the one generated by the LLM, they're actually logically equivalent. So can you say a bit on that?
Yeah. So we have a model M, the NLI model M, that is taking two inputs, essentially premise and hypothesis. However, we can like give it the hypothesis and the newly generated hypothesis as an input as well. And this will try to understand, does one entail the other or not? And in order to understand if something that we newly generated is equivalent to the original, we just give it to the NLI model and ask it to predict entailment, contradiction, or neutrality. And order here, of course, matters. That's why we say, does H entail H prime, where H is the original and H prime is the newly generated one? And does H prime entail H, where H prime is the newly generated example and H is the original? So if we have this symmetric equivalence, symmetric entailment in between them, we do consider them logically equivalent sentences in the eyes of the model that's being tested.
Got it. Okay. Yeah, understood. Thank you.
Yeah. Of course, we do testing for our method. We do automated set of tests. We see that there's like high token match, fuzzy token match in between the original and generated examples. The average length more or less remains the same throughout the examples, and there's like a big token overlap. Of course, this is not enough of itself. That's why we also do a random sample of 100 examples and ask two annotators to say, are these examples logically equivalent or not? And we see that in 99% of cases, the annotators say yes, and there's like a high agreement in between the annotators. So with this out of the picture, we should actually start to understand. Now, let's say we are able to generate this. What does it mean to evaluate for semantic sensitivity? Let's say we obtain the k-semantic variations for our original hypothesis. We test the semantic sensitivity of the model by replacing the original hypothesis with each of this newly generated adversarial hypothesis and making a prediction with the NLI model. And we use two metrics to measure semantic sensitivity within the NLI models, both of which are like derivative formulations of fooling rate. We essentially try to see if there was a label change. And we use like two very intuitive things for this. We say if the label was just changed, let's call it relaxed fooling rate. So if it was changed from the original prediction, then it's bad. We purely know it shouldn't happen. And then we also have like strict fooling rate. What if it's flipped towards an opposing class? So what if it was an entailment, but suddenly after like replacing, the model thinks it's a contradiction? It's like a much bigger leap of faith for the model to like directly flip the label. Neutrality, of course, does not have like a direct opposite. That's why we keep neutrality as is. We only compute this stuff for entailment and contradictions. Is the evaluating like paradigm more or less clear?
Yes, I think so.
Yeah, okay, sounds great. So the experimental setup is that we take models that are fine-tuned on MNLI, and we try to do it like a bit systematically. We take models of different architectures, more or less. We take Bart, Roberta, De Berta of different sizes, and then we also take models that were obtained through a distillation process. And we call training on MNLI and testing on MNLI testbed in-domain experiments, and training on MNLI and transferring our knowledge to SNLI and ANLI datasets as zero-shot transferring or out-of-domain setup. Okay, so this is like everything that we will be covering. So part one of the results: when and how do models fail? So if we purely look into like this very graph, there are like a lot of numbers. We kind of need to give a breakdown, but just eyeballing and looking up, we see that there are numbers that are like getting pretty unreasonably high for label changes. So let's just look purely step by step. So for in-domain experiments, meaning all the models were trained on MLI and testing on MLI, we see that the fooling rate on in-domain is reaching upwards of like 12.9, 16%, and essentially meaning that more than 50% of the examples have flipped the label after a very small change in surface form, which is very bad. And we know that more than half of those have been to a proportionally opposing class. Essentially, entailment changed to contradiction, contradiction changed to entailment in half of those cases. This kind of leads us to believe that minor semantic preserving changes lead to sizable shifts in model predictions. And this behavior is consistent across all the transformers we test. We can see that very much it happens for more or less to about the same degree in all of the transformers. This like makes us think that surface form variations hide the decision-making of NLI models, which is not something that we have known and not something that definitely should happen. So thus we have like a hypothesis here that we further test using the other experiments, that the models have very limited understanding of what semantic structure is and what does it mean to have logical relations and so on and so forth. So in order to test like this further, we say, okay, let's look at a more like lifelike setup where we have a model trained on a data set, however, tested on other similar but not exactly the same domain of data sets. This can be referred to as like zero-shot transfer or as like something like that. We refer to it as like out of domain. And we see that the effect in this type of settings is even more pronounced. We see that the models get perpetually worse the harder the set gets, and like that flips start to happen in like 50% of the cases, which is not something that we want to see. Essentially meaning that the original prediction that the model did was either like based on some type of a weird hack that it found on a data set, or was purely by chance. So semantic variations that caused a label change were likely originally predicted correctly as an inconsistent guess, because we see like the word inconsistent here means like it changed, and that is very bad. We also see like one thing, that more than half of the examples that did have a label change flipped the label to the exact opposite class, which is even bigger like cause for concern. Essentially like implying that we have zero idea about the logical structure of the sentence, about what happened.
This is very sad. So
Indeed.
essentially, we're saying that the large like these language models, the pre-trained language models, they have no clue about semantics practically. Like they just, you know, like they just find hacks, right, to classify correctly and so on, but they have like they don't understand anything really about the language.
Yeah, like they have very limited understanding of what does it mean to induce logical relations and meaning in between two sentences. And the capacity for that, assumably it should be there because, yeah, on all of these data sets, if we look into just pure numbers on like NLI, MNLI, they get like 90, 80,
Yeah,
like
yeah.
which is but suddenly like we introduced like this way one minor change and all of them crumble.
I mean, also it's interesting because don't you think this has implications to people that are trying to do reasoning with large language models, for example, in general? Because like imagine I'm trying to do a mathematical proof, or I'm trying to generate code, or something like that, right?
Yeah, it most definitely should. So the models that we tested, I think, are less than 2 billion parameters big. So we don't know like what exactly happens for much bigger models, like 7
Hmm.
billion, 13, 70, and upwards. However, what like several other researches on like larger models have found out that they're like much better at masking their behavior. For example, like we know this chain of thought thingy, like you might come to the correct answer and all your intermediate steps are wrong. Like so essentially I think the same problem more or less exists in the like larger language models, but it's a bit harder to test for. It's not like as straightforward as we do here. So, and we kind of like one like direction that I see for the future of this type of research is doing the same very systematically for large language models.
Well, large language, yeah. Okay, interesting,
Yeah.
interesting.
We also see that like the one interesting thing that we see is that we say, okay, let's see how does the distillation process affect the capabilities to like maintain and find this logical relations. And we see that if the model came from a larger model and is distilled, the effect is much more pronounced on it in terms of how sensitive it is to how not sensitive it is towards semantics. So we see a bigger drop, a bigger like label change, a bigger fooling rate for models that are distilled. While model accuracy remains comparable to the original model, the distilled version struggles sizably more with surface form variations. Essentially, it's uh, distilling does not necessarily allow us to transfer the even very limited knowledge that we had about like language understanding and semantics, and like it's kind of lost in between. That's what we're getting at right in here. And yeah, like the everything we said priorly remains the same. Like half of the flips are flips towards an opposing class. Then we say, okay, let's look at model size. Maybe our results like improve as the model gets bigger. So for in-domain setup, the relaxed rolling rate metrics marginally drop as the models get better, essentially meaning that, yeah, bigger models are kind of better at understanding, like at maintaining their original prediction in the face of semantic for surface form variations. But the same cannot be said for out of domain setup. So if you see the picture on the right, where we have like the base large and X large versions of the model, we see that on out of domain setup, X large is actually worse when in terms of the fooling rate, meaning that semantic capabilities are not only tied to the model size. Essentially, we can't simply claim that, yeah, increase the model size and you'll have a better semantic understanding. That's like one of the key things that we found out in this type of a setup.
Yeah, that's very interesting as well. So this is saying that the argument of just the scale, like and we're there, you're actually saying no, that is not the case. I mean, here's evidence for that.
Yeah, we say that's not necessarily the case. At least like scaling from like several hundred million to approximately like some billion, like 2 billion, is not going to be the trick. Maybe scaling towards like at one point there's like this exponential emergent capability, but
Mhm.
I think like recently there was this paper, which got a base paper in Europe, that says that essentially calling them emergent is wrong
Yeah, yeah,
because
yeah,
they don't suddenly appear. It's just like the metrics make us think that there's like this exponential increase, and if
yeah,
we
yeah,
change the metrics, it will become linear.
yeah,
So if that is true, like I don't know how to correlate this like power law to like that idea. Maybe essentially semantic like comprehension, the capabilities from semantic comprehension are not at all tied to model size. So maybe that's a thing that should be explored. But at least like what we claim is it's not that straightforward. Like going through like X10 parameters does not yield better performance for us on this type of a setup.
right. I mean, do you think it's related to how we train those models? Because I mean, to me, it's really interesting because semantic is like a structure, like it's a structural bias that we have in our language, in the data, and so on, right? And do you think we could remedy this problem by devising smarter loss functions that kind of induce that structure or try to learn that structure or so?
That's a great question. So, like, I also do agree that the way that we do, like, pre-training in particular, like, we do this, like, massive MLM plus regularization on all the models that we train from small to big. And MLM is a good task, don't get me wrong. Like, trying to predict, like, something from the context, some random word from the context is good in terms of understanding. But
Mm,
does it necessarily like create a space where like navigating which in terms of some type of a traversal logic search is meaningful is very dubious, at
mm,
least.
mm.
So we know like in terms of inner product, yeah, we can like do some finds, but in terms of can we essentially find a program that in a very, very old-fashioned word to vec is able to say like king minus man plus woman equals queen type of a
Yeah, yeah,
setup
yeah, yeah,
in
exactly. Yeah, yeah, interesting. Okay.
and I'm not sure. I do believe that maybe there is like a task that should be formulated better. Essentially, like it can be tied to the loss, it can be tied to how we represent data.
Yeah.
Maybe it's like MLM on steroids. I don't know.
Yeah, but I mean, also maybe architectures matter, no?
Most definitely. So I am like a big proponent of this belief that transformers are not the end of our like
Yeah, yeah,
our
yeah.
architectural search.
Mhm,
Most definitely. And I believe that some more like logical impositions have to be made
mhm,
into the structure of the architecture. Essentially, now the way we reason is that, yeah, which activations in the attention heads happen leads to some type of a hidden representation, which we try to nonlinear separate, which is good. Like it's better than what we had. But there is no explicitly defined logical structure to the way like we compute.
I agree.
Uh, yeah. So essentially maybe doing like this weird merge in between the symbolic methods like prolog and like other
Yeah,
search and this would yield the ultimate
makes sense.
like method. But yeah,
Yeah,
it's very much possible that your comment is the very reason. Maybe transformers are not the thing that like maybe they're just like very good at learning hacks.
yeah, yeah, makes sense.
Yeah.
Okay, so very interesting. Okay.
Yeah. And like we have the second part of the things where we say, okay, maybe we should check like, does the same effect happen across all of the labels? So maybe we're just like start to fail on entailment, but on everything else we get like more or less the same results, and we see something not shocking, but confirming our prior like assumptions and observations, where we know that across all of the classes, the effect stays the same. We see that in terms of relaxed and strict fooling rates, that the model is performing very similarly in terms of like, is it facing a problem where the original answer was an entailment, where the original answer was a contradiction, or was it neutral? This per class breakdown allows us to see that the effect is consistent. And the same effect applies as like we discussed like priorly for the out of domain and in domain setups, and for the distillation setup, everything else, everything remains the same. So the observed limitations in compositional semantic understanding are not caused by class imbalances, or like one class is not harder than the other, and it does not pertain to a particular label. So then we said, okay, let's go like even one level deeper. Let's look into the distribution shifts in decision making. So predicted distribution shift within the samples that cause changed model prediction. So first of all, we do this thing where we split the samples into two categories, considering whether the sample induced a change of the original prediction or if it did not induce a change. And by saying sample, I mean premise and adversarially generated hypothesis pair. And then we average the probability distribution of the labels obtained from the final softmax layer for these two categories. We compare both categories to the averaged label distribution from the original hypothesis. So essentially, in more intuitive terms, we want to say, if I were to compare exactly what's your decision bound, what's your like decision distribution, if the label change was caused and if it was not caused, how different would these distributions be? And we do this purely to understand, maybe like we caused like a small change and the model was not sure about the example from the very start. That's why maybe this effect that we're looking is not significant. However, what we observe through these two tests, in order to compare distributions, we use Jensen-Shannon divergence and Kolmogorov-Smirnov divergence. And we see that when a label is changed, it's almost exactly flipping the distribution towards something entirely different. So it's not like a small effect. It's a very massive effect that happens averaged out across all of the examples. So limited capabilities to utilize the syntactic information cause the model to significantly change the final prediction, given like this minor variations in the text. And despite the strong performance, there is masked degeneration in models stemming from limited semantic comprehension. So essentially, if we purely look at results without like this analysis, we will see, yeah, models are good, they're confident in their predictions. And then we look at this and we say, okay, what if I add like a random, like an other word like the? Eric went home, Eric went to the home, for example. I don't know how grammatical that is, but suddenly it just panics and shifts his decision to something in that like entirely disproportional with the original prediction, which is very bad.
Yeah, very bad. Interesting. I mean, this also reminds me a lot of these methods that are doing prompt engineering, you know? Like what we notice that when we look at the outputs they created, you start seeing weird characters in there.
Oh yeah.
That somehow, you know, like an exclamation mark, a hashtag, you know, whatever, and then suddenly it answers the question correctly, right? So it's interesting that you actually also see this in a more principled way, maybe. Yeah, this is interesting.
Yeah, it's actually like a very interesting thing regarding maybe the way that like the models were trained on the dataset.
Mm.
So for COT, we have this thing that if, for example, in context, we have examples and the correct answer is always A, and then we ask like, do COT on a new example, like given this everything, it will never say that, yeah, I answered A because all the answers I saw priorly were A. And for us, we have like a similar situations. So maybe every time in this data sets where he faces the world not, he knows, aha, contradiction. But and purely looking into results, maybe, yeah, like we see great model, but suddenly we replace the not with some more obscure variation of a not, and
Mm.
then it's like, yeah, we
That
don't
has no
see a
fit.
not. Yeah, yeah. And that's why like we have this like weird bias in them, and that is very masked in all types of
Mm.
the models from small to big.
Yeah, makes sense. Makes sense.
Yeah, and essentially the conclusion is that this is very scary, first of all. Because we don't really know how to counteract this unless like studies like ours account for larger language models and for like different phenomena from generation to classification. The thing you mentioned is very important. How sensitive are we towards the prompts? How do we take the attention from the prompts and the decoding process? Essentially, a lot of this like partly mechanistic, partly just explainable stuff that needs to be there as guardrails for us to understand what the hell are we doing.
Amazing, man. You really blew my mind. This is so cool work, actually.
Very much.
I mean, I love it. What I love about it is that it's such a principled way of measuring things, that lays down, the groundwork for a lot of weird claims people do, which is just amazing. I mean, this is so cool.
Thank you very
Is there a
much.
paper on this or so?
Oh yeah, yeah, yeah. Yeah. So we of course we do have our papers, our paper on this, which recently was uh, recognized as an outstanding paper. I should do humble bragging from now on.
Yeah, you should definitely.
So we got it into EACL. We got like an outstanding paper award there, and for everyone who cares, it's publicly available on Archive or on ACL domains, and it essentially lists what we did in a more like mathematical, more like step-by-step breakdown type of an approach.
And
But
is
the
the code
premise is the same.
is the code open source as well?
It is open source. We're just like cleaning it up just a bit to make it available for the general populace. But yeah, I think it's been resting on my Git for a quite long time.
No, great. And congrats on the outstanding paper
Thank
award. I
you.
mean,
Thank you.
that's why I mentioned this, because I knew about it, and I think you should brag about this. So congrats.
There's always this thing like, should I mention it and people will think that I'm like this very self-egocentric person, or should I not mention it and it goes down like
No, no. It's hard work. It's amazing work. It deserves it. It should definitely be mentioned. So
thank you.
this is awesome. Yeah. I mean, cool. So where do we go from there? Like, you think now we should look into how we resolve those issues, or um okay, what's your belief? I know it's a hard speculation question, but what's your belief? Do you believe if we go to large language models, those effects, like billions of parameters, right? Those effects will be less severe, or they will be the same? Like, what was your intuition?
So to the very least, they will be more masked. Like for that, we have a lot of evidence. There's a lot of stuff on what's known as unfaithfulness of large language models. There's the different ways to measure it. There is different ways to probe it. However, it's a lot harder because for a large language model, for example, I can't take this. I can't take this framework and purely say, yeah, a large language model passes this or not. Actually, that's something that I kind of want to do. I just didn't have the cycles to do yet. But I'm not convinced that like large language models will perform bad. And the bad part about it, it wouldn't mean that they're good at semantics. In the paper, I use this like very explicit wording. We say understanding semantics should minimally involve, like should minimally involve is the keyword.
Right,
Uh,
right, right, right.
so, so I do think that there is like this necessity to design this type of tests for them. And the people from my lab are actually like working on it day and night, and there are like attempts being made at it, but at least me, I haven't seen this like very systematic, very like grounded approach. Like we see the same effects across models, across different phenomena along the models. Like, does quantization somehow impact it? That's a big
Yes,
question for
exactly.
me.
Right. Yeah. Yeah, yeah. I mean, it's interesting. I also would be interested to see what happens with LoRa, like when
Yeah.
we start fine-tuning them with like low rank things, what's actually going on, like is it similar to the distillation behavior you saw, or what would we see, right? Yeah, this is very exciting. I mean,
Yeah.
cool, man. I love those types of papers, like it's so cool. It's like like to me, there's a lot of hype around LLMs today, right? And I think they can do some things pretty well, right? But I really like that you guys are trying, to be principled about it, and just like I mean, let's be sure, whatever is being said is actually true.
You know the very funny thing of how this research started, like so it was a complete like one-off for me at the at start, and it was tied to something entirely different a while back. And essentially what we were trying is using this like zero-shot classification that's based on the NLI models in this like, okay, if I give like the class a bit of a structure in terms of text, will it be able to predict it better? And we like found out like no way, unless it's like one word that's vaguely resembling something and the word is like important as well.
Wow.
So for it doesn't recognize negations at all. Like that's something that's more or less known, but it doesn't recognize structure at all. Then I was like, okay, we kind of need to prove this, like because I was more or less annoyed, and there's actually a very good paper on this that kind of inspired the whole endeavor. I think it was from EMNLP 2019. It received the best paper. It's called Unnatural Language Inference. Yes, I
Ah, okay.
remember.
Yeah, yeah.
And essentially, they said, what if we shuffle all of the words, more or
Yeah.
less, like create like versions of this shuffling and ask the model to generate with this shuffle? And they showed that, yeah, the performance doesn't get worse, which means like no one cares about like the word order.
Yeah, yeah, exactly. Which means there's no semantic knowledge whatsoever, really. I mean,
Yeah, and even lexical knowledge is like dubious of
even
how much of
lexical, yeah,
yeah.
yeah, yeah. Wow, amazing. Oh, cool, man. Cool work. Really impressive. I'm very excited, that you explained this to us. This is super cool. Typically, I end these interviews by one more question.
Sure.
And I mean, like there are like couple of people working on different things. So there's like, the ACL community and so on. There's the machine learning NeurIPS ICML community and so on. So how has your like reviewing experience been with the conferences? Like, because we know in machine learning, a lot of people are complaining that, we have bad review process. But I know in ACL they also have these special ways to review. So I mean, how has it been for you? Like, how has that experience been?
So by special ways, I think you mean ARR,
Yeah, yeah,
the new system. So I kind of do like the idea that there's like this rolling review and it like
yeah.
mitigates the pressure of the final deadline.
Mm,
Um, I don't think like the reviews have suffered, at least for me. I think it's an inherent there is like this inherent thing that we have with the current systems of like double blind reviews that
yeah,
they are rather noisy. And not because of the way we do it, but rather because no one is forced to follow up on rebuttals. Like I had like several situations. So funny fact. Uh, this very same research on I think like several months prior to our submission to EACL
mm,
uh, received such abysmally low stuff. Of course, we like iterated over the paper later on, but the general gist of the idea was the same. Like we iterated on the writing, on like how to present it better, a couple of more ablations, but nothing major. And the difference was like on average a score of 3 difference. So in between a 1 to 5 grading,
yeah,
which is very weird to see. And we like tried to defend us initially. And
mm,
the thing is like after you even address the comments that the reviewer posted,
yeah.
the reviewer is not obliged to answer. And they're like,
They're not
yeah,
obliged. No, no.
like that's why I, like when I review in particular, I like the rebuttal process even more than the um, process of actually writing the review because I, as a researcher, understand that there might be something that I missed, first of all, because usually for reviews, I would like to like take several days to actually review the research and everything that's connected to it, because maybe it's inherent knowledge that I don't have about
Mm,
the field for some reason. Uh, but if someone can actually convincingly like answer the questions I pose and convince me that no, you're kind of like oblivious to the stuff that we did, I'll be like very happy to hear that.
yeah,
And yeah, I think that's the most important thing. If doing rebuttals was like mandatory, I do believe that like the accuracy of what we do currently will improve massively, like
wow. Mm,
loads and leaps. It's just
this
like a
is
lot of pressure on the reviewer as well, but still, I do believe that that is something that should happen.
No. I mean, I fully agree with you because at the end, if the rebuttal is not going to be engaging, right, between the reviewers and the authors, then what's the point of a rebuttal? Yeah.
Yeah,
Then
yeah. I'm quite sure. Like you had like around the same experience. I would
I
believe.
agree. Yeah, exactly. Yeah, no, totally. I mean, they write something, then you write back, and then there was just no engagement, nothing back. And I'm like, okay, so I should assume from now on, if I get these scores, the paper is rejected, so I shouldn't spend time writing a rebuttal, really. Withdraw it and submit it somewhere else, right?
Yeah, yeah, exactly. I think a lot of like people that I respect kind of do it like that. They're like, yeah, didn't pass on the first time. We'll read if there's something like very uh like reasonable critique. Uh, but usually with these things, it's very weird. Like, so out of three, there's always one that's good. Like one, like regardless if it's negative, if it's positive, it's actually like something that gives you a point
Accurate,
of
yeah.
improvement. In my case, like the other two were usually like either misunderstanding of the paper or misunderstanding of the impact, which is again very hard thing to discuss. Like if someone says like, yeah, we don't think this is very impactful or this we don't think this is very novel, how do you counteract that?
Yeah. How do you do that? I mean,
My mom says I'm a great guy.
yeah. Yeah, you're right. I mean, it's very hard, like these arguments. Like, I don't know. Yeah. No, okay. I mean, fair. I mean, hopefully we can improve in the future, but
Oh yeah.
it's a tough one.
I think journals had it like have it done like very well. If they're like kind of inclined to take it, there's like this very long, months long, like iterations. Like they send new comments, you iterate, send the manuscript, but back and
Yeah,
forth.
exactly. Yeah, my experience with journals was much better as well, right? Yeah, I think I love the JMLR process. Like that was nice. You can submit, get feedback, submit again. Yeah, that's good. Let's see. I think it's also the sheer pressure on the system, right? Like everybody's doing, ML, AI today, right? It's like a lot of submissions as
Oh
well.
yeah, like this is the thing that like journals don't work for ML in general is that because they're painfully slow. Like they take like three to six if you're lucky months to get and
At
like
least, yeah.
yeah, and with everyone publishing on Archive yesterday, like
Yeah.
your research might be scooped like within not even in a span of weeks, in a span of days. I would
Days,
feel,
yeah,
to be
I
honest.
agree. No, totally. Well, makes sense. This was a lot of fun, Eric.
Yeah, it
Thank you
was
so
very.
much for coming. I really appreciate it.
Thank you very, very much for having me. It was an amazing talk and amazing time.
Thank you. All right. So, to our audience, thank you again for attending. Please like, share, and subscribe. And I will see you again with another episode of Mette with a Fantastic Researcher next time. So, thank you. And I will end it here.
Thank you. Bye.